Hello, everyone. My name is Dr. Hong Yeo. Currently, I'm an assistant professor of mechanical engineering and biomedical engineering and the director of Center for Human-Centric Interfaces and Engineering at Georgia Tech. It's my great pleasure to introduce my research regarding smart and connected software bioelectronics for wearable healthcare and performance monitoring. Before getting started, let me introduce my research group at Georgia Tech. We have a couple of postdocs, multiple graduate students, and more than 10 undergrad researchers. And as a team, we are working together and studying a few different aspects of soft materials, flexible mechanics, machine learning, electronics, and system packaging. So based on the fundamental research, we are developing a soft material-enabled electronics for wearable and implantable applications. So by using those soft electronic systems, we are trying to advance human healthcare, disease diagnosis, therapeutics, and persistent human-machine interfaces. But today, due to time constraint, I'm going to focusing on wearable electronics for athlete health and performance monitoring. You may wonder what is new and innovative features of soft material-enabled electronics. I believe this picture captures the novelty of soft electronics. So as you can see on the wrist, there are existing rigid-based wearable electronics made of rigid sensors and electronics, along with a soft wristband so that we can wear those devices. However, it's still using the rigid and bulky sensors. It still causes issues of discomfort, sensor contact, and long-term wearability and so on. Compared to that, as you can see that there's completely new electronics on the wrist, which was developed by my research group here at Georgia Tech, which is called soft electronics. So overall, the soft electronics offers an exceptionally smaller form factor and better skin compatibility with skin-like materials. And also it can offer better signals because of negligible motion artifacts compared to the rigid electronics. And also it has negligible thermal and mechanical burdens to the user. And overall, because of these aspects, the soft electronics can offer long-term wearability. Okay, so those are innovative factors of soft electronics. So based on these basic concepts of wearable soft bioelectronics, we developed this new system for reliable health, stress, and performance monitoring. So we are trying to target to use these devices for athletes. So I'm going to talk about that today, but if you are curious and if you want to get details, then please look at my published article shown over here. Okay, there are many athletes out there, and as time goes on, those athletes are, looking at new technologies because, their body strengths, their mental strengths are really important factors for them to, exceed their limit, physical limit and emotional limits and so on, so that they can perform the best on the field. So many people are interested in athletes' health and performance monitoring. Basically, we are trying to have a quantitative monitoring capability, right? So that you can give a feedback to those athletes. Also, we can have, feedback loop-based treatment and follow-ups to enhance their performance. So there's a question that whether we can quantitatively measure their health, stress, and performance. There are a few devices available out there in the market, as you may know. There's Apple Watch, wearable band, chest wearable belt or patches, and so on. Even though these devices are working, right? They are measuring, some of their health parameters, their performance metrics, things like that. However, there are still a lot of issues that needs to be addressed. First of all, it's not very comfortable to wear because they still use rigid sensors in electronics. So to have a good contact to the skin, they have to use straps or bands, things like that, or aggressive tapes or adhesives to make a good contact to push those sensors to the skin, which cause huge discomfort. At the same time, those rigid sensors have issues of slipping on the skin when body is moving, especially considering what they do in the field, right? So there's this motion issues that can cause a lot of artifacts for the signals. Because of those things, we are getting those lost data from continuous health and performance monitoring with existing devices. So to address those issues, here I developed a new method and systems called Wearable Flexible Hybrid Electronics, WFHE. So as shown in this example here, this guy is wearing this one of wearable flexible hybrid electronics, which is ultra thin, less than 5 millimeters in terms of thickness. It's ultra light, less than 5 grams with rechargeable battery. And as you can see that the form factor is very small, so it can be easily integrated, directly mounted on the skin without any aggressive tapes and straps and so on. This device has multiple layers that includes sensors and also the electronic circuits, so that we can measure those signals through the sensors, and also we can get those signals wirelessly based on Bluetooth to have the real-time simultaneous monitoring of those health and performance parameters. So one example here, we can measure heart rate from this photoplethysmogram data. At the same time, we can measure their acceleration, so that we can measure punch velocity, impact, force magnitudes, and many more. Then you may wonder how we can really fabricate these sensors and circuits. Among many different types of strategies, right? Here, we are using nanomaterial printing. It's called aerosol jet printing of nanomaterials. So basically, you can print any materials like polymers, conductors, semiconductors, and so on. So based on this method, we can make sensors flexible and stretchable, nanomembrane sensors and nanomembrane circuits, multiple layers of those circuits, and more. This picture here in this slide shows an example of nanomaterial printing. So here I'm printing a sensor based on silver and graphene, as you can see, based on this jetting, aerosol jetting process. We can basically draw sensor patterns or circuit patterns that we want. Okay, now we fabricate this wearable electronics and sensors. So we wanna compare the performance with commercial device. So here we have simultaneous comparison side to side of our sensor on the right-hand side and the commercial rigid wristband-based sensor on the left-hand side. And we measure the heart rate signals shown on the right. And as you can see, there are 3 graphs. Red graph shows rigid sensor-based data with ultra-tight securing. So we really push the sensor to the skin, and then we strap this wristband as much as we can so that it can have really good contact. So the RMS value is about 0.05. And without anything like that, any straps, purely based on the polymer natural adhesion, ultra thin, ultra light, flexible hybrid electronics shown in the blue line, has comparable signal quality to the commercial one, right? However, for the commercial one, once you have loosened strap contact of sensors to the skin, you can see immediate signal drop. And as you can imagine that, you cannot just fully secure and add forces to have contact of sensor to your skin in real world, because it's not going to be comfortable, and it can even block your natural blood flow. And another problem of rigid devices is that because of this rigidity and then area coverage, based on this thermal imaging data, as you can see that once you wear this device more than a few hours, you can see elevated temperature, which can cause skin irritation and allergic reaction and so on. However, compared to that, our ultra thin sensor, which is breathable at the same time, has no issues of temperature elevation. In addition to that, our electronics, right, the Bluetooth-based electronics can perform and record the data more than 10 meters between the sensor and the receiver, wireless receiver, right? And we are getting strong signals even under the glove with sensors. Okay. Another advantage of our sensor is that we can have negligible motion artifacts compared to the rigid sensor. As I said, there's a slipping between rigid sensor and soft skin, which is shown on the red line. However, the blue curve from wearable electronics shows negligible noise compared to those rigid wristband devices. Here, this video shows how it looks like, right? So this subject is wearing two devices at the same time and running on the treadmill. And the insert shows real-time data of heart rate and motion acceleration. As you can see that on the left-hand side, that's the wristband device, which has high motion artifacts, 0.16 voltage. However, on the right-hand side, which is based on flexible wearable electronics, has negligible motion artifacts, which is about 0.06 voltage. Okay, then in terms of signal processing and data acquisition, we develop our own method called sparse signal reconstruction, so that we can look at both heart rate data and motion data. And then based on the accelerometer data, we know where those motion artifacts coming when we measure heart rate, so that we can extract that, as shown on the right, so they can purely measure the heart rate with specific frequency domain. So we compare this measured heart rate from our sensor with the gold standard electrocardiogram-based heart rate, which is shown on the blue, and our sensor is shown as red. And as you can see, they are having really good matching each other during rest, walking, and another rest condition. And also, even a subject is running, right? As I said, with our device, we have negligible motion artifacts. That's why we can get really good data recording of heart rate, which is comparable to ECG sensors. So far, I talked about an example to measure heart rate and motion acceleration. With the same device, we can measure other parameters like human stress. Okay, it's one of those metrics that we want to measure from athletes because it's naturally related to their performance. It's really important to measure their emotional stress and condition, right? So here, we are trying to measure the stress levels via measuring galvanic skin response, which is also called electrodermal activity. So stress, when a person is stressed, then there's a body response activated, meaning that blood is rushed to the peripheral of the body, so which can change the conductivity of the skin. So by using a pair of electrode, we can measure that conductivity change, which is called galvanic skin response. So to do that, we modify the previous WFHE by adding a pair of electrode at the bottom of the circuit and layers, right? As you can see that. So that you can measure the conductivity change over time. At the same time, we added the temperature sensor to compensate any environmental changes of temperature to measure the GSR values. So this is how we can measure those stress data. Okay, on the bottom left, as you see, our device is on the right, on the wrist. Also, you can measure those data on the shoulder as well. Try to see the performance of our device. We compare the device performance with other gold standard commercial devices, PIP on the fingers and BioRadio. And top left, the blue lines are showing the commercial devices. You see the change of data from relaxed and stressed condition, which is comparable to something that you can measure, skin-like electronics on the wrist, right? And that's the raw signals, and then we go through signal processing through filtering and peak threshold calculation so that you can identify stress peaks, which is shown on the right, right? So you can clearly see the number of peaks are completely different between a relaxed condition, the green side, and stress condition on the red side, right? And also you can see that's really happening, validated by PIP commercial sensor. Okay, and then we summarize how we can measure the stress values on the wrist, shoulder, and we compare that with commercial devices on the finger. And as compared between relaxed and stress, you see clear difference of those number of peaks measured by our sensors. And even though overall signal amplitude is less than the commercial devices, but at the same time, we can lower the background noise so that the overall device performance is very compatible to commercial systems like BioRadio or PIP device. Right. So with that, I'm thinking that, based on this type of wearable, flexible hybrid electronics can work as a next generation health and performance monitor. So one day we can see, next generation Floyd Mayweather, even though he's retired, right? So new emerging guy who can wear this type of ultra thin wearable device on the wrist or chest or other locations. So when they are working or when they are practicing or when they are doing those matching, we can measure their physical conditions and others to have follow-ups in real time. Okay, with that, I'd like to summarize my talk today. I briefly introduce materials manufacturing method, signal processing, and system integration for smart and connected bioelectronics. And then this example as on wearable health performance monitor. I'd like to thank you for your attention, and I'll be happy to answer any questions. At the same time, you can email me if you have any questions, or you can visit my website to see more activities in my research group. Thank you.